All right, here we have lesson 10, which is going to be about spontaneous reactions. So, we previously learned that a spontaneous reaction is a reaction that happens without additional work being supplied after the activation energy is met, right? So, the reaction will occur on its own without that additional work being added. So, some questions that I want you to think about is what types of reactions do you think will be spontaneous, right? So, not all reactions will occur, okay? Not all of them will be spontaneous. So, are exothermic or endothermic reactions more likely to be spontaneous? And how about ones that there's an increase in entropy of the system or a decrease in entropy of the system? So these are some of the questions that we're going to be trying to answer today as we look at spontaneous reactions. So let's start by looking at our enthalpy changes and see how that affects our entropy. So let's say a reaction is exothermic, meaning heat is released from the system. It will increase the entropy of the surroundings by increasing the temperature of the surroundings. Okay, so remember, our enthalpy is our heat that is being released in this case, and entropy is the amount of disorder. So we're saying that when heat is released, the disorder or the entropy will increase of the surroundings. So an example is, let's say we take a coffee cup, and we know that when we leave a hot cup of coffee, it will spontaneously cool down. Well, we know that heat will be released from the system to the surroundings, right? Exothermic. And as we can see in our diagram on the right, our coffee cup is very, very contained, right? It's very ordered, okay? But as soon as some heat releases to the surroundings, then it becomes more dispersed, okay? There's more disorder. Okay, so exothermic would give us more entropy in the surroundings, an increase in entropy. So when a reaction is exothermic, it has a negative delta H, and it contributes to the entropy of the surroundings and is more likely to be spontaneous. What we can say is the change in entropy of the surroundings is approximately equal to the change in enthalpy of the system. Exothermic reactions also lead to a decrease in enthalpy for the system and an increase in stability. However, IB would like you to think about this in terms of entropy. Okay, so when we have an exothermic reaction and we release heat, the entropy of the surroundings is going to increase. When a reaction leads to an increase in entropy to the system with a positive delta S, it is more likely to be spontaneous according to the second law of thermodynamics, right? So remember that we're talking about how the entropy is always increasing in the universe. Okay, so we have this positive change in entropy, and that would mean a more spontaneous reaction when we can increase that entropy. Now, temperature plays a big role as well. So the effect of the change in enthalpy in the system to entropy of the surroundings is very much related to the temperature of the surroundings. Let's say we have a higher temperature, which would mean more disorder and therefore a higher entropy. But we also need to take into account what kind of temperature do we already have if heat is being released. Well, if the surroundings are already at a high temperature, the heat released makes very little difference in the disorder, right? It's already high, so a little bit of heat is not going to make much difference. But if the surroundings are at a low temperature, the heat release can have a huge effect on the disorder, on the difference of the disorder. Okay, so what we could say is the increase in entropy or the change in entropy of the surroundings is approximately equal to 1 over T. If we combine that with the previous slide, then we have the change in entropy of the surroundings is equal to the negative delta H of the system divided by T. And now I'm going to be getting into a bunch of equations that are all going to combine into one. So I don't want you to get too confused with all of this explanation because it is coming to one main point. Now let's consider total entropy changes when looking at a reaction and whether it will be spontaneous according to the second law of thermodynamics. We need to realize that the second law applies to the universe, not just the system we are observing. So the total change in entropy is equal to the system and the surroundings. So both of those are added together, and that must be greater than 0 in order for it to be a spontaneous change. We want the entropy to increase. So we can input or substitute the equation from the previous slide to get the total entropy or total change in entropy, combining the entropy of the system with the enthalpy of the system as well as temperature. Now what this all leads to is if we rearrange the last equation, we get Gibbs free energy, which is given by the letter G, a state function that combines enthalpy, entropy, and temperature of a system that can help us determine if a reaction is going to be spontaneous. Okay, so with a little math manipulation, we get our final comparison where delta G, or our change in Gibbs energy, is equal to delta H minus T delta S, and that must be less than 0, which means that the change in Gibbs free energy, or delta G, must be negative for a spontaneous reaction. Okay, this is the main point I want you to take away. That equation was manipulated to get delta G by itself. And that leads us to the Gibbs free energy equation. Delta G equals delta H minus T delta S. This is the equation that you need to know. If delta G is less than 0, the reaction is spontaneous. If delta G is greater than 0, the reaction is not spontaneous. Okay, so this combines delta H and delta S along with temperature. So whereas delta H is a measure of the quantity, the amount of heat changed during a chemical reaction, delta G gives a measure of the quality of the energy available. It is a measure of the energy which is free to do useful work rather than just leave a system as heat. Okay, so in order to determine if a reaction is spontaneous, we must take into account the enthalpy change, the entropy change, and the temperature. All three of those play a role. All right, this is the main equation you have to know. And if delta G is less than 0, then the reaction is spontaneous. If delta G is greater than 0, the reaction is not spontaneous. So let's do some practice questions, okay, where we can take that Gibbs free energy equation into account. So let's start by looking at something that we all know, right, which is water. And I want you to give an equation for the boiling of water. Okay, well, if we're boiling water, we're going to turn it from a liquid into a gas. So we have H2O in the liquid state, turning into H2O in the gaseous state. Predict a sign for the enthalpy change and the entropy change for this process. Okay, so we have enthalpy and we have entropy. Okay, let's start with entropy. Okay, so from our equation that we see here, we're going from a liquid which is ordered to a gas which is more disordered. So since we are increasing the number of moles of our gas, we say that delta S is positive. And now let's consider delta H. Okay, the enthalpy. Well, in order to go from a liquid to a gas, we have to add heat, right? And we have to break those intermolecular hydrogen bonds. So therefore, delta H is also going to be positive. Okay, so you can see the answer for letter B there. Letter C says predictive value for the sign of delta G at low and high temperatures. Okay, so in order to do this, we have to remember that delta G equals delta H minus T delta S. All right, so that's our equation for Gibbs free energy. Now, when we have really low temperatures, okay, let's say 0, okay, low temperature would be considered 0. Well, if we have T being equal to 0, then this is going to go away. If T is equal to 0 or really, really low, this value here is going to be so small compared to delta H that it's not going to be significant. So at low temperatures, delta G is equal to delta H, and that means it's going to be positive. Okay? But now let's say we have high temperatures. Okay, at high temperatures, if I put in my equation again, at high temperatures, this subtracting value is going to basically be much more significant than this delta H, and delta H is not going to make a difference. So at high temperatures, delta G is equal to negative T delta S. Okay, so there we see at low temperatures, delta G is approximately equal to delta H, and so is positive. Whereas at high temperatures, delta G is equal to negative T delta S, and so is negative. Okay, so we can see that temperature does play a big role in determining whether a reaction will be spontaneous or not spontaneous. All right, letter D, suggest why water boils at 100 degrees Celsius. Okay, one of the things I want you to remember is when we're considering delta G, we mentioned it's greater than 0 or less than 0, whether it's spontaneous or not spontaneous. Well, at 0, that is when it's at equilibrium. This is something we will learn at a later time. But if delta G is equal to 0 and we're at equilibrium, that is when water is boiling. Okay, so we need to have delta G equal to 0. In this case, it's going to occur at 100 degrees Celsius. And as we will see here, the change only occurs at higher temperatures where delta G is negative. So at 100 degrees Celsius, delta G is equal to 0. And that would mean that anything higher, delta G is negative, and we'll have our spontaneous reaction. Okay, now we're going to add some numbers in. Okay, this will be the main thing. is we have our Gibbs free energy equation, and from that we can calculate delta H and delta S and then combine them all together. So in letter F, it says use the data below to calculate the enthalpy change for the process. Okay, so we're given the delta H of formation for our liquid water and our gaseous water. Okay, so hopefully you remember delta H of formation Sorry, I actually skipped letter E, where we have to use the entropy values in the table below to calculate the entropy change for this process. Okay, so on the right-hand side, we are going to actually use the delta S values, okay, which from the previous equation, you have to do products minus reactants. So when we go ahead and take a look, we are given our values, we do products minus reactants, so we would do 188.8 minus 70, and that would give us 118.8 joules per Kelvin per mole. Okay, so in order to find delta S, you must do sum of the products minus sum of the reactants. Since we only have one product and one reactant, that's easy enough to just subtract the two, taking into account any number of moles. Take note of the unit, which is joules per Kelvin per mole. And then if we go back, this is where we're going to do letter F, where we're going to do enthalpy change. So we do delta H, which again, we're going to do products minus reactants. So we would do negative 242 minus a negative 286, and that gives us a positive 44 kilojoules per mole. Okay, one thing I want you to take note, delta H is kilojoules per mole. Delta S is joules per Kelvin per mole. Okay, take note of those different units, because that's going to play a role in our final question. Deduce the boiling point of water from your calculations and describe any assumptions you have made. Okay, well, we know that delta G equals delta H minus T delta S. Well, at the boiling point of water, delta G is equal to 0. So from this equation, we know that delta H is going to be equal to T delta S. Right? If all of this is equal to 0, we can just add this to the other side and get delta H equals T delta S. And if we want to find the boiling point, which would be our temperature, temperature is going to be equal to delta H divided by delta S. Right? And we just calculated delta H and delta S in the previous question. When we do the math, this is where the units play a big role. We cannot just divide 44 and 118.8 because the units won't divide. So as we'll see in the answer here, we input the 44 kilojoules per mole, but for the delta S, since it was in joules, we just have to convert it to kilojoules by dividing it by 1,000, or what they've done here is multiplying it by 10 to the negative third. By doing this, we can see that kilojoules will cancel and mole to the negative 1 will cancel, leaving us with 1 divided by K to the negative 1, which is equal to K. So at this point, the temperature would be 370 Kelvin when you divide those two numbers. And one of the assumptions that we are doing is assumed that the delta H and the delta S do not change with temperature. Okay? That is an assumption that we are making. All right, let's do a couple more of multiple choice and short answer questions to wrap this up. So ammonium chloride dissolves in water spontaneously in an endothermic process. Identify the best explanation for these observations. Okay, so we know from our lab, right, that ammonium chloride, NH4Cl, is endothermic. Okay, well, we know that endothermic processes are not energetically favorable, so we can cross that out. The bonds in solid NH4Cl are very weak. Well, that's not true. We have our ionic lattice. We also have some strong covalent bonds, so they are in fact quite strong. So it must come down to the entropy changes. And we want to know which one. Does the system drive the process, or does the surroundings drive the process? Okay, well, in this case, it's the entropy change of the system that drives the process. Okay, the entropy change of our system is the one that gives this a spontaneous reaction. Okay, let's look at number 63, two-part question. In letter A, we want to use data from section 12 of the IB data booklet and additional data. So we have the enthalpy change of formation for solid water. And we want to calculate the enthalpy change that occurs when ice melts. Okay, well, in order for ice to melt, it has to go from a solid to a liquid. So we can write down that equation. So they've given us the enthalpy of formation of the solid, so we can look in the IB data booklet for the enthalpy of formation of the liquid, okay, which is negative 286 kilojoules per mole. So if we wanted to find the enthalpy change, remember, enthalpy change for enthalpies of formation means we take the products minus the reactants. So the product would be negative 286, and we're going to subtract a negative 292 to give us an overall enthalpy change of positive 6 kilojoules per mole. Okay, so we do products minus reactants. That gives us that positive 6. In letter B, it says the entropy change when ice melts is 22.0 joules per Kelvin per mole. So that is our delta S. That is our entropy change. Okay, it's given in joules. That means we have to take that number and divide it by 1,000. Or we can take this number, the enthalpy change, and multiply it by 1,000. Okay, you have to do one or the other. Okay, don't do both. Choose whichever one, and you will get the right answer. So deduce a value for the melting point. Okay, so we want to find the melting point. That would be a temperature. We did that on the previous slide where the temperature equals delta H over delta S, and we will see where they multiplied the enthalpy change by 1,000 to get it to joules. And when you do that, you would get 273 Kelvin. Okay, so ice melts at essentially 0 degrees Celsius, or 273 Kelvin. In number 64 and number 65, these are very, very, very similar questions. So if we answer one, we're going to be able to automatically answer the other one. So let's look at 64. It says, identify the combination of delta H and delta S, which results in a reaction being spontaneous at low temperatures, but non-spontaneous at higher temperatures. In number 65, it is the opposite type of question. So let's just stick with number 64. So spontaneous at low temperatures. Okay, so spontaneous means delta G is less than 0. And then non-spontaneous at higher temperatures, and that would mean delta G is greater than 0. Okay, so we know our spontaneity values, but now we have to look at the temperature. So we know that delta G equals delta H minus T delta S. Okay, let's look at the first part of the question. Spontaneous at low temperatures. So in order to get spontaneous, we need delta G to be less than 0, which means we need this value to be negative. We need delta G to be negative. Okay, well, we know that it is a low temperature. Okay, so if we have a low temperature, okay, at low temperatures, T delta S is very, very small. Okay, it doesn't really matter what the temperature is. It is a small value, which means it is not going to play a role in our value. Okay, so we can essentially ignore that. Well, if we want delta G to be negative, then we must need negative enthalpy. So at low temperature, we need delta H to be negative in order for it to be spontaneous. Okay, so that automatically excludes C and D. Okay, so at a low temperature, this second part of the equation, T delta S, is going to be very small and insignificant compared to the enthalpy change. So if we want a negative delta G, we need a negative delta H. Now let's look at the second part of the equation. Okay, we need non-spontaneous at higher temperatures. So again, I'm going to write my delta G equals delta H minus T delta S. So at high temperature, we know that T delta S is going to be quite big. Okay, it's going to be very large, which means that this second part of the equation is going to overpower the first part where it does not play a role. So at a high temperature, T delta S is going to overpower the delta H, and we want delta G to be non-spontaneous, which means we want a positive delta G, which means we need a value that will make this negative T delta S, we have to make it positive. Well, temperature is always going to be positive, so in order to make this negative T delta S positive, we must make negative delta S, it must also be negative. That means A is our answer. Okay, I know this question might be a bit confusing, but if you just remember the Gibbs free energy equation and look at low temperature versus high temperature, that will help you determine positive or negative. Okay, number 65 is just the opposite of 64. Okay, this one's asking not spontaneous at low temperatures, but becomes spontaneous at higher temperatures. So if delta S and delta H were both negative before, here they're both going to be positive. Okay, we have two more questions. The delta H and delta S values for the combustion of hydrogen are both negative, which is the correct description of this reaction at different temperatures. Okay, so we have delta G equals delta H minus T delta S. That is our Gibbs free energy equation. So it says delta H is negative and delta S is also negative. Okay, well, let's look at a low versus a high temperature. Okay, at low temperature, right? Remember, this second part is not going to play a role. At low temperature, delta G equals delta H. So if delta H is negative, then delta G is going to be negative. And if delta G is negative, that means we have a spontaneous reaction. So at low temperature, it's spontaneous. So we have two options left. Now let's look at high temperature. At a high temperature, delta G equals negative T delta S. We know that delta S is already negative. So if we're multiplying a negative delta S times a negative T, then delta G is going to be positive. And that would be not spontaneous. So that means B is our answer. And finally, number 67. The decomposition of limestone can be represented by the equation. Okay, seen there. Predict a sign for the enthalpy change. Okay, well, in order to decompose this reaction, energy must be added. Heat must be added. So delta H is going to be positive. In letter B, predict a sign for the entropy change. Okay, hopefully you notice that in the equation, we are taking something that is solid and producing a gas. So there's an increase in the amount of gas produced, which would give us a positive delta S. So we have enthalpy change is positive, entropy change is positive. And in letter C, we want to deduce how the stability of limestone changes with temperature. Okay, it always comes back to this Gibbs free energy equation. Okay, so deduce how the stability of limestone changes with temperature. At low temperatures, delta G equals delta H, and therefore delta G is going to be positive because delta H is positive. At a high temperature, delta G equals negative T delta S, and so it is negative because the entropy change is positive. So if delta S is positive and T is positive, then the overall entropy or Gibbs free energy is going to be negative. So what we can tell is the reaction is not spontaneous at low temperatures, but becomes spontaneous at high temperatures. That is because delta G is positive at low temperatures, so not spontaneous, and delta G is negative at high temperatures and therefore spontaneous.